May I call upon Dr. A. Limaros, Department of Mathematics, to introduce the keynote speaker. Dr. M.S. Jagadish Kumar, Head of the Department of Mathematics, Vellore Institute of Technology.
Good morning to all. It is both a privilege and a delight to be here today as we gather for this prestigious international conference. Our gathering is graced by the presence of a truly remarkable individual, our esteemed keynote speaker, Dr. M.S. Jagadish Kumar, whose insights and expertise promise to inspire, educate, and elevate our conference experience. As we embark on this journey of intellectual exploration and collaboration, it is important to recognize the pivotal role that keynote speakers play in shaping the discourse and setting the tone for our discussions. Today, we are fortunate to have a speaker, Dr. M.S. Jagadish Kumar, who embodies the spirit of innovation and excellence. Dr. M.S. Jagadish Kumar is a head and professor in mathematics at School of Advanced Sciences, VIT, Vellore, India. He holds an MTech degree in atmospheric sciences and an MPhil degree in mathematics. He obtained a PhD degree in mathematics from the University of Kerala. He is a consultant for a leading multinational R&D organization and carried out many research projects. He delivered several talks at national, international conferences and workshops. He has association with various foreign universities as visiting professor China, Ethiopia, and etc. He won several awards, honors, and to list a few. Silver Medal Award for MTech, Cochin University of Science and Technology in 2001. MSMR, Senior Research Fellowship, Delhi. Professor Murthy Award, IIT Kharagpur. Honorable mention in USA. He serves as Research Fellow, ISRO Bangalore and ISRO Trivandrum. He is a life member of ISTE, ISTEM, and IMS. He was the Vice President and Acting Joint Secretary at IIT Kharagpur. He has published several publications in various reputed national and international journals. Today, we are privileged to have the speaker, Dr. M.S. Jagadish Kumar, who serves as a beacon of knowledge and who embodies his role with the unparalleled excellence. Our keynote speaker's journey and accomplishment are the testament to his dedication, passion, and relentless pursuit of excellence in his field. His insights have the potential to ignite creativity, stimulate innovation, and drive us toward a brighter and more promising future. Once again, on behalf of Icrtmcs 2023, I extend our heartfelt welcome to our distinguished keynote speaker, Dr. M.S. Jagadish Kumar. Thank you for gracing us with your presence and sharing your invaluable insights. Let us warmly welcome our keynote speaker to the stage with a round of applause. Over to you, sir.
Hello.
Thank you, ma'am. Dr. M.S. Jagadish Kumar, the stage is yours.
Respected Principal, Vice Principal, Organizing Secretary. Of this conference, Sister Santiago Teresa, all the speakers, Dr. Kasem A. Saleh, Dr. Anthony Xavier, Dr. Pir Basha, I'm sorry, Dr. J. Sabaskar, and all other dignitaries, faculty colleagues, and my dear students. Very good morning. Of course, I thought that I'll first talk to you, then I'll come to my presentation. Since I didn't get a chance in the beginning, so let me address you 5 minutes. I'm standing this as a practicing mathematician. I use the word intentionally, practicing mathematicians, because you have heard the word practicing only with the doctors. They practice medicine after a registration. If they pass out from the medical college, then you have to get a registration with some oath, like I'll just do justice to this profession and with sincerity. But you can be a mathematician, just get a degree, start doing it, that's all. But we never practice mathematics. We learn, teach, understand, a lot of things we are doing. But I'm posing a question, why can't you become a practicing mathematician? Then there is a huge demand for that, huge demand for that. Because everyone around you want math. They want to learn, they want to understand, they want to improve their system. But still, the era is like we have a lot of technology, but still we are using maybe less than 5% of what math can do. Even less than 5% of math can do. Only maybe scientists, maybe some engineers, they are using the support of mathematics. But every field, you can do that. Now, I'm just taking you back to 1983. Something happened in India. Can you remember what it is? Yes, 1983, we won the World Cup cricket. It is not a small thing. It changed the fate of India. It united India because of this small game. That time it was new to us. Some people are playing game cricket. Then when we won first time World Cup, it come to the notice of all the people. Then everyone started playing. I was in 83, I was in school. So we started playing cricket because of Kapil Dev or Gavaskar or the people of that kind. Then everyone started playing, irrespective of city or village. Then we have talented people. We have a pool of talented people. Getting into Indian team is a big task now. So we have a wonderful team, a performer. After 40 years, one more thing has happened. That is in 2023, August 23. What is the importance? We have landed in moon, soft landing. 40 years after that. This again united India. We, all the scientists, all the engineers, all the people in this realm of knowledge, they unite together to understand, to explore how ISR has made this one. Up to that, ISR was here. I was in ISR for some time. I got a chance to interact with these people. I feel that was the finest moment in my life. I know how these people are working, how serious they are, how dedicated they are. But you think about the journey where they have started. They started just with a small rocket, small piece of rocket, just which is available in shops now, kind of thing. Then they are simply test firing those things to collect data, then moving from place to place, understanding, simulating. Then they failed several times. The failure was more. That is why it came as a success now. Failure was more. We fire the rocket, it will not go to the destination. Several years, every Wednesday, we used to launch rocket, Rohini rocket. This is just a Sonde rocket, just to collect information from the atmosphere. It will go to several kilometers, collect the information, then we just keep it in magnetic tape. It is still kept in ISR and Space Physics Laboratory where I have worked. We don't have this kind of sophisticated technologies to store information. Today, I'm going to talk about how to store information. We don't have sophisticated technology. We have just like in magnetic tape, we just copy information. One magnetic tape, you can just you cannot even copy the information what you are storing in a small pen drive. Like tons of magnetic tapes still kept in the storerooms of ISRO. Of course, they are not using it because they already coded those things and safeguarded it. I'm talking about technology was not developed to that extent. ISRO started working. Their first vehicle was a cycle. To transport things from place to place, it was a cycle. The rocket part, they taking the cycle. You have seen this one, Dr. Abdul Kalam and team. and they sat in the in out, I mean, in the greenery, then started discussing, not in AC rooms and all. Then why we are failing several times in all, when I was in school, all the mimicry and mono acts, one theme is about ISRO. Like they are launching their rocket, it's just going to Arabian Sea or Indian Ocean, like that. So lot of humiliation, lot of criticism. People started asking, why you are spending this much of amount? They are simply spoiling on 400 crores. What you are spending is not meaningful when people are starving. This was the question. But still people have the energy to proceed. And finally we succeed. So what we want is persistence and perseverance. Now today I'm very happy that I'm in a village where an institution is working and they are conducting their first conference. Like what has happened in 83, what has happened in 2023. Here for you, at least this conference is very much important. This is going to change your fate. I'm sure about this one. This is going to change your fate. What is happening? At least 5 people get motivated out of this one. They gathered together. They started discussing. It will spread like a fire. It will spread like a fire and attract a lot of people. That will strengthen your program. So, and whatever amount you are spending, whatever the effort you are putting for this one, it become an added advantage for you. It will come back to you. So conference or gathering or discussions, whatever it may be, even the percentage of dissemination may be less, but it will make a difference. That changes the fate of the institution. That was what happened those days about cricket, about, the activities of ISRO, the soft landing, what has happened. But the target group is different. So I'm telling, like, you should understand what we are going to speak, not 100%. I'm going to speak a few things which came to my mind and what the new research area I have chosen. So try to understand it to your level. You may not get everything because you cannot learn everything within 1 hour. But try to understand what it is. Go explore. Keep on working on that. Like that. I attended my first conference in 2001 when I was in Cochin University of Science and Technology. I was sitting in the last row. I used to tell this one. I was sitting in the last row, but I was one of the organizers because day and night we are moving for this and that. Then we'll sit and enjoy what presentation is going on. But friend, if you sit in the front, everyone will listen to you. This is our tendency. Then when I was sitting there, people started talking about Indian monsoon, then talking about dynamics, fluid dynamics, some transport equation. So the particular talk, he was explaining the transport equation at different dimension. Then slowly I was sitting there, then I raised my head. After some time, I come and sit in front. Then I came friend. After the talk is over, I met the scientist. Then we have a interaction, the Professor Ramanathan. So we had a very deep interaction that kindled my interest on this one. That is why I choose my research topic as mathematical modeling. Otherwise, I got a fellowship in IIT Delhi for continuing my PhD in atmospheric science. I didn't join because of several reasons, but still I want to do my PhD in mathematical modeling. I struggled a lot for that, but finally I did it. Finally I did it because there was a consistent effort for that. I don't want to do in any other domain. You can publish a lot in certain domain, but still I have the satisfaction that I have learned something in the domain what we want. First of all, I want to be a mathematician. I want to be a mathematician. If today I'm asking, someone asks a question that what you are proud of, I'll say, I learned mathematics. Not just about my degree. My parents asked me to learn mathematics. I did it. I learned a lot of mathematics, not in terms of degree. Whatever you give, even my colleagues, you can see that. We are all proud of being a mathematician. Had I got an admission in computer science when computer science a lucrative subject in 1992. I lost the admission because there is high competition for that. I lost the admission for a few marks. I have a lot of, pain that time because of the reservation system and kind of thing. I didn't get admitted in first 14, only 14 seats in merit. That day I was thinking, oh, I lost this opportunity. But later when we started mathematics, started thinking about mathematics, today we are very proud of being a mathematician. I want to tell you that whatever your capacity of learning mathematics, every time you have to improve. There was an era that India has created a lot of mathematicians. Even the concepts created by this Ramanujan was still not understood correctly. There are a lot of undisclosed work still not proven, but which is true. So we are the part of this legacy. So definitely we want to do better. I am the head of the Department of Mathematics. So definitely, without talking about my department, this talk will not be complete. We have 133 member faculties in the Department of Mathematics. 133. Whenever I say there, sir, are you talking about number of students? No, I'm talking about number of students. Is it for the whole university? No, in my department. This 133 faculty members, all PhDs with outstanding publications, with very good credentials, with very good potential. We have published 548 publications in the past 5 years in Science Citation Index Extended. Altogether, 1,000 plus publication we had. So this has not just came. You should understand the way we are working. We are not just working for the sake of working, but we enjoy every moment in working as a group. I have my professor here who was part of my team. So you can ask him how we work. So I'm telling you that you love something, then you will not count for time and other things like that. Just love doing it, organizing, conducting, interacting. What do you get if you go at home and sleep? Nothing. What you get if you just explore in Facebook? You explore 5 minutes, 10 minutes, 1 hour, 25 hour, 10 hour, no problem. You define it, but it's not control you. You learn something, learn yourself, and enjoy the concept. I'm talking about not about university degrees, because I met one I cannot call him as a professor, one researcher in the University of Kerala. He is a clerk. He used to come to our department, very simple dressed. So initially we were saying what this man is going to do here, because when you are in university, we feel that, oh, we have degrees. And at that time I was an FFL student. What is this clerical man who, to do this one? He gave a seminar. I still remember the seminar that is on magic squares. Magic squares. I have a great respect on him. He published several papers without a university degree. He published several papers in American Mathematical Society, in which I have not published even. Several papers he have published in American, because the order of work what he is doing is very, very potential. So anyone can do. You don't need a university degree for that. You don't need the support of anyone. Just love the concept. Start reading from the scratch, and follow your passion. How persistence and perseverance. One day you will success, like how this ISRO has soft landed in moon. This percentage of failure is small, 90% failure chance. But ISRO took all the options. Plan A, Plan B, Plan C, because this time we have to success. Recently, there was a meeting with NASA. Now NASA is asking the technology of ISRO. There was a time America has introduced sanction on our institutions. Now they are asking the technology, because to develop the same technology, they have to spend 2 lakh crore rupees. 1 year working capital, 2 lakh crore. It's a huge amount. But ISRO is spending, total budget is 13,000 crores. Where is 13,000 crores and where is this one? That is the thing. We have a lot of talented people across us. You please understand, I'm coming from a place called Kollam. The ISRO director, he is Dr. Somanath. He studied in a small college called Tangal Kunji Musliar College of Engineering, TKM College of Engineering. One of the best college in India, I can say. But still I'm seeing from outside vicinity, it's a small college. It looks like a small college. It has not gone from that stage, but it has produced a lot of outstanding people. He used to come over there, and proudly, we are all associated. I didn't speak to him. I didn't see him also, but every time he used to come and see, he used to come to his alma mater with proud feeling that I learned the concept from there. So he grown from because of his persistence and perseverance. If you get some energy out of this conference, I'll be very happy. With these few words, let me get into my talk. I think this is working. Hello, can you hear me? Hello, can you hear me? Hello. fine. Otherwise, I'll hold. Hello? Hello? Is it fine? This is my institution, the mascot of our institution. There are several buildings. If you find time, come as a team. You are always welcome. Yeah, my talk is on decomposition of matrices and its application. Let me tell why I chose this topic. I'm basically a fluid dynamist. I do solve fluid dynamics problem, model it, and get the output prediction on all those things. Particularly, I'm working in porous medium. You can see two things here. One is 5 plus root 5 by 2. The value is 1.618. What is the importance of this? This is called the golden ratio. Golden ratio. Why golden ratio is important? You read this one. You know about Galileo Galilei, who invented telescope. From here, he was watching moon and seeing the minute things of moon. When 500 years before, 500 or 600 years before, he has done this one. The great enthusiast, he told, nature is written in the language of mathematics. If you ask mathematics, we say a lot. When you say a lot, that means you don't know anything. If you talk with clarity, you will not say a lot. You just specifically say the applications. This is, you see, nature. Nature is so beautiful. So beautiful. This ratio is kept in the universe. That's why nature is beautiful. Everywhere. I'm just telling he's very beautiful. He's very Adonish. So meaning is all his proportion. This length by this breadth. If you just measure and find, it converges to this number, 1.618. This is Fibonacci sequence. You know about Fibonacci sequence? What is that? 1, 0, 1, 1. Then this two are added together. 2, then 3. Then sum is 5. 5 plus 3 is 8. This is Fibonacci sequence. Simply speaking, yn plus 1 is equal to yn plus 2. With the initial condition, this is initial condition. Yn is 0, yn plus n is 1. When you solve, you will get this answer. So this sequence, this you can represent in this way. And you see this ratio. Sorry, this is not the solution, of course, or not the solution. When you take the ratio, what is the ratio? It will converge to this one. 1 by 1, 1, 2 by 1, sorry, 2 by 1. Sorry, 1 by 2. Like that, this ratio, when you take, it will converge to this one. Actually, this is the number, the sequence, the nature is built. For example, you take a sapling. You know about sapling. Okay. So first leaf will come. First, no 0 leaves. Then 1 leaf will come. Another leaf will come. What the angle? One will come. Opposite side, nothing is there. Then another one will come. Totally 180 degrees. Sorry, 360 degrees. Then opposite side, 2 leaves will come. Then you can see 3 will come. Then 5 will come. You go and count. You can see that. Why it is so? Because of photosynthesis. Because the distribution of sunlight should be equal. All should get an opportunity to get the energy equally. That's why this distribution. So this kind of mathematics is embedded in all the phenomena in nature. Whatever you take, there is some mathematics embedded inside. This is one of the things. So we can identify. You just see a butterfly. How it is being designed. There are thousands of designs of butterflies. Beautiful. What is the measure of beauty? So everywhere some mathematical things are. You see the nature, the hills, the landscape. By default, for years, the landscape will come, which follows the mathematics. Only things you have to unveil. Pi. What is pi? It is circumference divided by. What is pi? Circumference of a circle divided by diameter. That is pi. That's a magic number. Because you cannot write that number in a paper. You can say only approximately. So the nature is built of a lot of mathematics. And I'm just going to explore some mathematics behind the natural things. What is this? First mobile phone. I had a friend He is very spendthrift. In 1991, he got a mobile phone of this. What is the cost? Approximately 3 lakhs that time. 3 lakhs that time. He sold the property and got this one. Because, and he hold like this in bus. He goes like that because the mobile this much, hold like this one. So everyone knows that he's rich. And you know, to make a call, 10 rupees, receiving is 10 rupees. And someone who's enemy, they will call for 20 minutes. Finish, your pocket is. So this was the technology initially we had. Then we improved to this one. This is again Motorola. The Nokia came into picture. You can see this one. What is this? Antenna. This antenna is much bigger. I cannot put this, so that's why I cut this figure. This antenna is smaller. Technology improved. This is much, mobile phone is much smaller. And then antenna is small. Screen is white. The screen, nothing. You simply, screen, it's not appearing here. When you put in your telephone, usual telephone, number will not come. That technology. Here it appeared. Whatever you type here, it will come here. Now antenna is inside. Antenna is there. It is inside. Small antenna, very powerful antenna. So antenna technology has improved. This one, again, digital display and all these things, much improved version. I'm not an expert to tell, but if I explore, I can say what is the difference between this model. So this is the evolution. This is the evolution. Everything, math inside. Math inside. You heard Intel inside. Am I right? You heard Intel inside. Math inside. Otherwise, this will not have improved. Have you seen the first computer? Have you seen the first computer? It is much bigger than this room. If I just consider this a room, with all the cubes and that kind of thing like that. Then chips. So thousands of chips inside a computer. The first kind of computer I was using, 286 model, it will take 5 minutes to switch on. We switch on and go and take a tea and come. That much time it take. Now you just switch on the mobile phone or sorry, your computer and start working. That's all. Even we are not happy. We are not happy. It's taking too much time, 5 seconds. I cannot tolerate. I want fraction of second. That's what I'm going for high rated computers and all. The amount you are spending, first time I used laptop in ISRO, it was 3 lakhs. Now laptop for even 20,000, 50,000. That's it. It is not the same laptop. That was capacity. Now it is very, we can say super computer of 80s. That kind of thing you are getting for 50,000 rupees. Technology improved just because of mathematics, not because of physics. Physics is there, definitely it is there. But all these things, size reduced. Physics plus mathematics, I can say. Okay, this again, small antenna. I don't know why this antenna has come, I don't know explanation, but something more. You see here, you can see a color screen. It is not painted. It can send color images. It can read color images and all. It's not a small shift. To get the face Nokia phone, I was in queue for 1 hour, nearly 1 hour in Trivandrum. Because Nokia first time introduced the color phone. To buy that 7,500 rupees. I didn't remember the number. To get this particular phone, I was in the queue for 1 hour, almost. Because there is a huge demand. Everyone wants a color phone. And that I had thrown after 2 years. Because the new phone came. Then after that, we have smartphone. Smartphone is different. Smartphone is a computer, which you can keep in the pocket. Previously, it is called laptop or something like that. Now it is pocket top, which turned as a mobile phone. So I'm just going to tell you what has happened. This is the latest iPhone. iPhone Pro Max. What's the price? Lakhs. Lakhs. So we have a dream to buy this. We won't buy. Even if you have money, we won't buy. Why should you spend? That's our attitude. Having a lot of features. But everything math inside, ultimately. See this one? This is a mobile phone. I'm sorry. This is a mobile phone. This one, you see? Antenna inside. How this transmits signals. How mobile phone works. You send some, you just have a conversation. That will be converted as electromagnetic waves. That will pass through some cables. Previously, it's just through a cable, some signals are going. Now, optical signals are going. What is optical signals? It will travel the speed of light. It is so fast. So, optical fiber technology came. Then we have a series of networks. Looks like a cell. That is why it is called cellular phone. Body cell, how it is arranged. The entire universe is arranged like cells. So, from shifting to one cell to another cell, mathematics support a lot. That's why we are able to succeed in this particular technology of mobile phone. Then you have a lot of You have a chip inside. This chip, it has the concept of Boolean algebra, correct? Otherwise, it will not work. And lot of math inside. And you have pixels, colors, and material. I'm going to talk about this today. What the pixel means, what the role of matrix is, and what is the role of colors, how you create all these things like that. You are all using WhatsApp, correct? When do you start using? 2010 onwards? No, you are not born that time, is it? 2014, 15, we started using it. Now without WhatsApp, without Dosha, I can leave. But without WhatsApp, I cannot do. I'm not using flash drive at all. I just use WhatsApp because their server is very fast and kind of thing like that. Everything we use WhatsApp or Facebook or Insta. That's it. That's why the technology has changed. But just because of mathematics. I'm talking about this part, but you can see that even you type something here. I'm just saying, how are you if I type? How it appears here? It is just numerical concepts. I mean, mathematical concepts. It will be, whatever you type, it becomes converted as code. That is called ASCII code, American Standard Code. So for each alphabet, there is a number. Whatever, each character, there is a number. That number will be transmitted. Number means easily you can do that. You just take the binary form. That binary form you can convert as current, correct? 0 or 1. Then we just create bits and then we can convert. These are basic principles, you know. So a lot of other things, it can be even used as a calculator. I'm going to talk how this facility has improved. Because in WhatsApp, what you do, you can send a video. Have you imagined in 2011 how you send a video? You have to download the video, you have to attach with some mail. There is no mechanism to send it through mobile phones. And even color picture you cannot send. Picture you cannot send. Then how will you send color picture? So now we have any color picture, anything, simply you can send just because of the contribution of mathematics. You see, it's all about matrices. You know about this professor? He's a professor in MIT, Massachusetts Institute, a dream place. His name is Gilbert Stein. He is the professor who made this area popular. The domain of matrices, linear algebra, popular by Professor Gilbert Stein. Because up to that, we just discuss about linear algebraic theorems. Lot of theorems in the book. You know that in any classroom, teachers will come and teach theorems. They never say how to apply it. But he just made popular by telling the application. So we refer his books. Even I learned this concept referring his book. Linear algebra, Gilbert Stein and David Seeley. I'll come to that later. This is a matrix. What is a matrix? You know what is a matrix. Teachers will come. Everything arranged in row and column. That's a matrix. But your understanding should be much better. I'll just tell in a different way. It is matrix. I can easily find out the height of P3, the weight of P4, if I arrange in row and column. But this is, suppose P1 is a person, you have thousands of information about a person, we can encrypt here. And for me, that is a vector. When I say a vector, you say a quantity having magnitude and direction. But for me, it is something like information encrypted to a particular individual. It may be a person, incident, whatever it may be, or institution. Is it? So this is one-dimensional. I write as a vector. This is row vector, sorry, column vector. So we write as a column, or you can represent as a point like this one. 1, 50, 4, 1. What is this? A point. You write a point. This is a point in fourth dimensional space. Or you can write second one, P2, 0.94030, etc. Ultimately, in n-dimensional space, you can map it. I'm sorry. Yeah. Now I want to speak about eigenvalues and eigenvectors, without which I cannot proceed. Basic concept. How many of you know eigenvalues and eigenvectors? Please raise your hand. The concept of eigenvalue and eigenvector. You cannot come to that one. Many concepts I know. You please understand. We have an n by n matrix. We have lambda, a non-zero scalar. Then this equation, this is an equation. Ax is equal to lambda times x. What is that? Ax is equal to lambda times x. What is Ax of matrix? So when you apply on this matrix, apply on this vector, that will be transferred as the same vector. X is a vector, like this one. When you apply, it becomes lambda times x. Not coming. Can you hear? Okay. Can you hear? Okay. It's fine. So, hello. Hello. Please. So this equation is very, very important. The say AX times sir. AX is equal to lambda times X. That means X is transferred using a matrix and to get the same vector X. But lambda times X. You have a vector X. What is lambda times X? It is extended or shrink. Extended or shrink. So this says all the vectors which is magnified. Instead of extended, we say magnified. Okay, so that value is called, magnification value is called eigenvalue. And this vector is called eigenvector. What is the physical meaning of this? What exactly when you find a eigenvalue, you see here, you have 1, 2, 3, 4, 5 points. This is my matrix. Please listen. This is my matrix. When I apply the transformation, the coordinate gets changed. It's a new transformation, new thing. So this is another axis. So this point, I have given the transformation here. 0, 0. If, for example, 9, 4, 4, 3, apply on this vector, multiplication vector, row with column, you will get these two formulae. When you substitute the values of P and Q, you will get these points. 0, 0 means 0, 0, 1, 0 means 9, 4, 0, 1 means 4, 3, 0, minus 1 means 4, minus 4, 3. All these points under this transformation, I plotted here. So I got this one. And if I plot all the points on the circle, I get all the points on this ellipse. This is a transformation. So first you have to understand what is a transformation. I'll explain in a better way. This minus 1, 2. What is minus 1, 2? X direction minus 1, Y direction 2. This is X direction 2, Y direction 1. So that point under this mapping transferred to these two vectors. You can calculate it here. So this vector is not changed. It is 1. Magnification factor is 1. But this vector changed to 11 times. 11 times. That is the eigenvalue. So if you solve the equation X is equal to lambda X, lambda is the factor of shrinking or expanding. So some vectors will not change under the transformation. And that magnification factor is lambda. The vector which will not change. After vector is not changed. This is the direction, this is the direction. But direction did not change, same direction. But it got magnified. This is very much required in image processing because image is a matrix. Image is a matrix. You want to enlarge, you want to shrink without changing the characteristic. A human picture you are taking and extending, characteristics will not change. Your nose alone is expanding, nothing else is expanding. How it look like? You lose the characteristic. So in image processing, in image compression, we want this concept of eigenvalue and eigenvector. Hope you understood this one. And there is a concept called diagonalization. Diagonalization. In diagonalization, what we do, we have a matrix. We apply transformation, some transformation, then you will get another matrix which is having only diagonal element. That is the eigenvalue. So this process is called diagonalization. There are many techniques for that. One is similarity transformation, another one is orthogonal transformation. There are several theorems supporting this one. You won't understand everything. Try to understand a bit. So the theorem says, if A is a real symmetric matrix, real means elements are from real numbers, symmetric means A transpose is A. If A is a real symmetric matrix, then if you follow this process, find the eigenvalues, find the eigenvectors, put in the form of model matrix, then normalize it. Normalize means divide with the magnitude. Then N transpose AN will be a diagonal matrix. This is the process for diagonalization. This is applied everywhere. So you get a diagonal matrix. Diagonal matrix means diagonal entries are eigenvalues. That's why I say D, lambda 1, lambda 2, lambda n. Then the problem is, now let me make it simple. I have an image. This image I will just make into some partitions we call pixels. So pixel means m by n matrix. If it is a square matrix, you can think about a transpose and all. A transpose is A kind of thing. But if it is not a square matrix, what you do? The answer is here. You won't do directly. You just go for A into A transpose and A transpose into A. What is A into A transpose? It's a A into A transpose is a symmetric matrix, correct? This A transpose into A is also a symmetric matrix. Then whatever process you have done in the previous stage, we repeat here. So you will get U as well as V. U as well as V. Then you write A in terms of U sigma V transpose. This is a beautiful decomposition. You will understand it later. A you can write in the form of U sigma V transpose. This U is a rotation. U is rotate image. There is some board. I have written something upside down. You cannot read it. You change it. That is a transformation. That is exactly a transformation. You rotate it. And it's too small. You extend it. That's it. You use a lens. That's what happening. Your image will be extended. You can read it. So linear transformation we are discussing about. Either rotation or stretching or compressing. So what is important about transformation? When you do transformation, you can easily understand things. That's all. Throughout our life, we are doing transformations. Even you writing some note, it's a transformation. Textbook, we are very difficult to understand. Your own language, you are transforming it. Is it? I'm talking about linear transformation. Line become line. That's it. You are rotating, line become line. You are extending, line become line. So it is linear transformation ultimately. So if you decompose A as U sigma V transpose, this U is the normalized model matrix of A into A transpose. V is the normalized model matrix of A transpose into A. This sigma, this is very important. This is compression or dilation. You are stretching it or you are shrinking it. It is embedded inside. So I'll just talk about this one. And I just talk about the rotation, you know, how to rotate something. XY is a point. We call it as a vector. So if you want to transform this, you see here theta rotation. This axis will become x dash. So you are rotating theta degree. So this is the rotation matrix. This is a standard thing. Cos theta minus sin theta, cos theta. So theta rotation, the point will change accordingly. You put this value of theta, multiply with x, the new xy will come. That's the meaning. You have old xy, a point. You put the value of theta, multiply it, you'll get the new point under this transformation. So this is about rotation. Now I'll speak about transformation. So far, you are seeing only numbers. You are thinking about matrices, very difficult to understand. Now only figures. You may be much more interested. See this one. What is this? Dog. Lab. Lab, is it? Okay. Can we transform this image without losing the characteristic? I want to make a bigger, you are daily doing. Copying, pasting somewhere, extending, arranging with BPT and all. This is linear transformation. Okay. What is this? Horizontal stretching. You got an elongated dog. What about this one? Compression. Your dog is like this. Are you doing this kind of exercise? Yes. What about this one? Vertical stretching. What about this one? Vertical compression. Your dog look like this one. But the characteristic is not losing. When you compress a dog, you will not get a human. You can identify the features. So as an image, when you process, you should not lose it. What about this one? Rotating it. Anti-clockwise. I think your clock is running in this direction, not opposite direction. So you can rotate in any direction. Now you just forget about dog. I have a circle there. I want to get this image. Can you do this? What you are supposed to do? Easy. From here to here, it is easy. Do 1 plus 2 plus 3. What is 1? Horizontal stretching. Horizontal stretching. Forget about this, the last figure. I have stretched horizontally. This circle, I have stretched horizontally. Then vertical compression. From top, I just compressed it. Then rotation. So I got this one. So this is the way I reached to this figure. Is it clear? What about this? Problem is much complicated because I have more information. Information 1, information 2. This is called rank of a matrix. In classroom, you have studied rank. What is the rank of a matrix? Rank is the order of the highest order, non-zero, minor. Confusing. That's why you are struggling, failing the exam. But if you learn rank, the characters inside a collection of data is rank. So we are trying to form in the form of a matrix. There are two information. One is blue, another one is this one. I have a lot of other colors. That is a rank. Here rank is 2. If I make a matrix here, rank is 2. I am sure about this. I want to attain this one. Can anyone tell how to attain this one? Stretching, shrinking, vertical compression, rotating and all. How to achieve? Yes, this is the way. Is it 1 plus 2 plus 3? No. Because 1 is this one. Horizontal stretching, you will get this one. Then vertical compression, you will get this one. Clockwise rotation, you will get this one. Here, blue color is upside. Here it is downside. You did not get the image. Suppose I am with a blue dress and saffron pant, then it will upside down. Is it? So this operation, this is transformation. Is not the right transformation. Then what is the right transformation? This is the one. 1 plus 2 plus 3 plus 4. What is that? Clockwise rotation. This is the image. I just clockwise rotation I made. So that's why the clockwise rotation came like this. Next, horizontal stretching. Then vertical compression. Look at this. Use your own brain. Then clockwise rotation. So we came to the right image. Yes, similar image. If you do this much operations, then you will come this one. That is what you have seen. What you have seen previously. U, sigma, V transpose. U is rotation, right rotation. Sigma is all about stretching or compressing. Then V transpose, that is again rotation, different direction, suitable direction. But when you speak and talk like that, when you really want to do something, you have to apply math because precision is very, very important. What does this have to do with matrices? Sorry, film show is over. We are going to mathematics again. Lot of math. What is this? 3, 0, 4, 5 is a matrix. So 3, I'm taking 4 points. You forget about this. This is matrix. I'm taking 4 points in my plane. One is blue, red, green as saffron. Then PQ is point. When you multiply A with this vector V, this is column vector. You will get this one, this formula. Row with column operation, you will get this one. Suppose the point is 1, 0, you will get 3, 4. 0, 1 means you will get 0, 5. Minus 1, 0 means you will get minus 3, minus 4. 0, minus 1 means 0, minus 5. These points I mapped under this transform. This is the transformation matrix. Transformation matrix. So I will get these 4 points. I can map all the points here in the circle. I will get the ellipse. Yeah, exactly this one. I have done only with these points, but if I consider all these points, this is the new shape I am getting. If I use this matrix is embedded with compression, rotation, all these things. We don't know. From this, we are taking out how much you have to compress, how much you have to dilate, how much you have to rotate, anti-clockwise, clockwise. All this information is inside. There was a time matrix is simple matrix for us. Now we know how much we have to do, how much you have to extend. When you do in computer, you are not doing it, you are simply stretching it, correct? You copy some image, just stretch from the corner. It's happening. It's happening because of this theoretical concept. What about this? This is about rotation. If you want a theta rotation, I already done this one. So cos theta minus sin theta cos theta. If this minus sign comes here, the rotation is opposite. This minus sign comes here, it becomes opposite rotation. Okay? That's it. Now you see, the sigma is called singular value. Singular value is the square root of eigenvalue. So that decides how much you have to extend. Singular eigenvalue decide how much it is magnified, how much it is shrink. Singular value design actually it is connected with the eigenvalue, but this is the singular value we say. Hence we apply a concept called singular value decomposition. Singular, I am talking about singular value decomposition now. So the sigma is the extent you are stretching in one direction. This is stretching in another direction. It will come in the diagonal. I talked about diagonalization. When you apply diagonalization, what you are getting is lambda. But when you apply this concept, you are getting sigma. Sigma is the amount you have to stretch. It's not like unknowingly you are stretching. When you do in your laptop, you can decide. When you are programming something, you have to tell. You stretch up to this one only exactly because you are writing algorithm. So you should know at what value you have to take decisions. So think about this image now. Sigma 1, sigma 2. It talk about extensions. Yeah, this thing, 1 second. We'll go to the next one. Yeah, here. All the things together. A is the matrix constituted of rotation, dilation, compression, and anti-clockwise rotation. What we have shown in figure previously. But same thing mathematically. So this matrix, this is the given matrix. Then this is U. This is rotation I told. This is sigma. This is sigma 1 is the one dilation. This may be compression. This is another rotation. U, sigma, V transpose. I'll tell you how to calculate that. I'm just now talking about singular value decomposition. Same thing, already just mentioned. You have to split this matrix into U, sigma, V transpose. What is the process? Consider A into A transpose. Find the normalized model matrix U. Find the A transpose into A. Find the normalized model matrix. Find sigma and write in the capital sigma. Sigma means sigma 1, sigma 2, then put in this form. It is a diagonal matrix. All these things together, when you multiply, you will get A. So A is decomposed in this format. It is decomposed in this format. Okay. The same example, 1 second. I have done this computation, it's a small matrix. I calculated normalized model matrix of A into A transpose. That is U. This is U. I calculated normalized model matrix of A transpose into A. That is this one. I calculated eigenvalues and put the root. It is this one. When I put these things together, when I multiply, I will get A. I am telling every time now, this one. This is nothing but rotation. Because cos theta, sin theta, minus sin theta, cos theta. When you can find theta, theta is minus 45 degree. When you put this as cos theta, sin theta, minus sin theta, cos theta, theta values minus 45 degree. So this part says you have to rotate the image. This part says you have to stretch to 3√5. This say you have to compress to √5. 1 is the actual thing. If you less than 1 means compression. More than 1 means dilation, stretching. So this say √5 times you have to stretch. This is again another rotation. I will come to the next stage. You see, this part is over. 3√5 times horizontal scaling. You have to extend this 3√5 times. This means √5 times you have to extend. Not extend, actually compression. You see the next slide. √5 times. This means √5 times. The previous figure, this figure, and this figure. There is difference, you know. There is difference because of this factor. And see the next one. I'm coming to the first part, this one. So the angle I calculate, it is 71.72 degree. So if you rotate 71.72 degree, you will get exactly this figure. So mathematically, I know how much rotation, how much stretching, how much shrinking, all these things. This is very much important for computer science students as well as mathematics students. You should understand this. That's it. I'm talking about all this thing. First, we have rotation, then stretching, shrinking. Then we have another rotation. We'll come to this form. It's a collective form. Then there is another concept called dimensionality reduction. Dimensionality reduction. You know Indian flag. How many colors? Tricolor. If you don't see the chakra inside, the chakra has a different color. Only three color. The rank of the matrix, if you take these three, because rank means you just make the pixels, boxes, each box one color. So maximum three color is coming. So rank of the matrix is 3. If you have several colors, rank is several. Sometimes 50, 100. It's very difficult to handle those things. If rank is less, you means only less information you have to transform. 3. If you want to send the Indian flag, it is easy. Tricolor you want to send, easy. Only 3 color you give the information, it will recreate the image there. So data processing is very simple. So that is the importance of dimensionality reduction. When you handle very huge data, you have to compress it. So if we want to store the data, you have to compress. I told that previously we are storing the information in floppy disk. Now we have digital sophisticated technology to compress it. That's why you are able to store 1 tera in small pen drive. 1 tera you can store in pen drive, small in, because of this kind of technology. I'm not talking about the technology is advanced. Much more things are there. That's behind it. Now you see, once again, what is this matrix? 1.8, correct? 1.2, 4.4, 4.6. What is the rank of this matrix? 2. Why? Because first row is not similar to second row. Whenever you multiply first row, you will not get the second row. If first row is a multiple of second row, we call rank is 1. This rank is 2. What about this one? 1.8, 1.2, 4.4, 4.6. I have done all the calculation. What is the calculation? I have decomposed, matrix decomposed. U, sigma, V transpose. You don't think about all these things. Understand you have to do some mathematical computation to split this A into U, sigma, V transpose. That is defined. You can refer book and do that things. But I'm telling like that time, this is what I am getting sigma. This is my sigma. Sigma consists of sigma 1 and sigma 2. You see sigma 1, that is dilation. I have to expand the image 6.71 times. What is this one? 0.44. That is vertical compression. Less than 1 means compression. So you are some point less than 0.5 you are compressing. If you don't compress, what will happen? My image, you are compressing a little bit. If you are not compressing, what will happen? You don't get any additional feature. You can ignore it. So when this is very small, you can ignore it. If you ignore, then computation is somewhat less. You need only this one. This 0.44 compression you can avoid. So that's what I'm telling. Now you see, here I make 0. I make 0. Then when I make 0, something happened with this matrix. What is happening is, rank is 1. Now you see, 1.5, 1.5, 4.5, 4.5. First row is a duplication of second row. Or 3 times. When you multiply first row with 3, you will get the second row. That means second row is a multiple of first row. They mean they are dependent vectors. So I need to send only one information, my first row. Second row is a duplication. Correct? Ultimately, what is happening? This dilation, this compression is 0. So if you want to, I don't want to compress, means you start with this matrix. This is called dimensionality reduction. Because the previous matrix is this one. 1.8, 1.2, 4.4, 4.6. Suppose you have a 1000 by 1000 matrix. The rank is 1000. Rank is 1000. But by applying this technique, small change you are making, so your computation will be considerably less. But you will get the same image without much difference. Small things we are neglecting. So to get more accuracy, small accuracy, you have to do a lot of computation, lot of transmission facilities. So if you apply logical mathematics, then dimension of the data you can reduce. This is the importance of dimensionality reduction. So by applying the concept here, I got this matrix. So I instead of the previous matrix, I only need to use this matrix. There are several techniques of dimensionality reduction. Now currently I am working on this part. What is a better algorithm for dimensionality reduction? Without losing the features. With a better algorithm, how to send information. You heard about Chandrayaan. You have enjoyed the photo. Chandrayaan, after this rover came out, 12 hours they kept it silent because there are lunar dust. When lunar dust came, he came and took photos. That photo came next day. A small photo came. It is just a photo, but it is a proud moment that we got a first photo from Chandrayaan, this moon. What is the importance of that photo? It is not, they explained in a news report, they explain it is not an easy thing to send. People are thinking that time by time they will send it. To send one image of that kind, it took 6 hours because it is 3 lakhs kilometers. So that image, without losing its characteristic, with a limited facility, it should be sent to Hassan, where we have a center for receiving this one. Then you have to process the image. Only signals are coming, weak signals are coming. That weak signals we have to process. We have to extract all the information rank. The correct rank you have to take in. Then only you get a picture. Suppose it is a color image. It's not a color image. It's a color image full of beautiful colors. It will take a lot of time. So you have to improve your technology. Even now, this is an open problem. Tomorrow you are coming with the technology that you can send the speed. You can send an image with the 3 hours, great contribution. You will be absorbed in ISRO. The one who is doing the computer program, who designed all these things in ISRO, is having only BSc qualification. Just BSc. You don't have an MTech, you don't have a PhD. He joined ISRO long back, all the brains, all the concepts, all the mathematics. The team is working, of course, but he is the brain behind that one. So if you have an idea, this lifelong this algorithm will be not in your name. So this kind of process, dimensionality reduction, new technique you can introduce, it's an open problem. It will save crores of rupees. This technology, if you go to NASA, their 2 crore annual expense will reduce to 1.77 crores, maybe, who knows? So technology matters. So this is rank 1 metrics, I mean. So in nutshell, this is rank 2 metrics. We reduce rank 1 metrics. But your data is huge. It is 10,000 by 10,000. When you reduce, it may be 50 by 50. I will explain it in a different way. Look at this. Can you see these values? 1, 2, 3, 4. What is this? -1, -2, -3. It is when I multiply this with -1, I got this one. That's why I put -1 here. 2. If you multiply first row with 2, you'll get this one. With the 10, when you multiply, you'll get this one. So all these are multiples of first row. Am I right? Second row is a multiple of first row. Third row is a multiple of first row. Fourth row is a multiple of first row. So I need to write only these two, the column and this row. So that is this column and this row. So instead of sending this matrix, I need to send only this information. Then you say you multiply and get the value. Suppose this is 10,000 by 10,000 matrix. Then you need only 10,000 plus 10,000. What is 10,000 plus 10,000? 20,000. You send 20,000 data. What is 10,000 into 10,000? Huge number, huge number. You don't need to send that much of information. To send that much of information, you have to pay. You have the bandwidth. You have time. Your computer will be. That's it. So instead of, because of this technique, this become rank 1 matrix. So you need to send only row and column information. It's just 8 number. So that way you'll save time. Suppose this is a different thing. What is the rank? This may be rank 1, 2, 3, 4 by 4. What is this one? I cannot write simply like this one. Previous case in a single step I have written, but I cannot write now. What I do is, I write as a sum of 1 by 1 matrix. Rank 1 matrix. This is rank 1 matrix. Next one is rank 1 matrix. See, here it is rank 1 matrix, correct? This is rank 1 matrix. So I wrote like this one. Similarly, if it is any matrix, you write it as a sum of rank 1 matrix plus rank 1 matrix plus rank 1 matrix. That is nothing but your U sigma V transpose. It is, when you expand that, it exactly comes like this one. It is a sum of rank 1 matrix. Some rank you don't need to send. Ignore it. Color is not important. I have a blue, which I have a small dot with a violet color, indigo color. What is the need I have to send the indigo color? You will notice that I will compromise. Reduce the, make it as 49. Like that, information which is not relevant, you have to suppress it. That's it. That is actually in practical cases, dimensionality reduction. Yes, this is what I told. Any matrix you write in terms of rank 1 matrix. This is rank 1, this is rank 1, and so on. That is nothing but this one. I told you sigma U, sigma V transpose. When you split row by column, it will come like this. This is sigma 1. This is the amount which you are enlarging. This is rotation. This is another rotation, part of that rotation. So when you split, it will come in this form of a matrix. So is some sigma, this is as a descending order. Large, medium, small, tiny. Last example I told, if the contribution of sigma 4 is very less, delete that. If the contribution is small, delete that. So you will get the image. That's it. This is applicable for transmitting the image as well as storing the image. So this is with a computation. Previously I just told it. Now this is a matrix. I computed U, I computed sigma, I computed V transpose. When I split a row with column operation, I'll get this one. This sigma, when you multiply this one, sigma 1 times, 21.2 times. Next one, 6.4 times, 4.9 times, 0.1 times. When you do this matrix multiplication, you'll get like this one. So this alone you take, this is the computation. When you completely calculate, this is the value. When you completely calculate, this is the value. When you add these things together, this is the value, not alone this one. If you take only this term, this is the values. If you take this plus term, this is the value. If you add this term, this is the value. If you add all the values, it is the same matrix. 3, 1, 4, 1. All this value, it is exact match. This is very close to this one. So we want only close values in image processing. That's it. I can spend another 5 minutes, 2 minutes. That's it. Suppose it is not a square matrix, not a problem. Because we are not bothered about square matrix and all. We simply think about A into A transpose and A transpose into A. Now I'm just talking about another 2-3 minutes I'll take. This is about image processing. You have some information, you have to compress it, you have to either store or you have to transmit. Then you have to retrieve it. You have to decompose it and you have to retrieve it. That's it. Now in actual image processing, what is happening? Image is a matrix. That matrix you just divide into rows and columns. Each row has some color. When if it is a black and white image, we say grayscale. Pure black is 1, pure white is 0, or vice versa. A small shade of black is called grayscale. Like that, 256 grayscales are there. What is the importance of 256? 2 to the power of 8. 2 to the power of 8. So all these colors are marked with 1, 2, 3, like that. So when you divide an image, you can give some number with that particular color. Just come here. Here. This is actually a digital image of a heart. If it's not continuous. So this is black, this is white, only 2 colors. So when I make in the form of a matrix, black become 1, white becomes 0. That's it. So I can just create this matrix. That whatever matrix are available, I just made this computer U, sigma, V transpose. This is first computation. This is second computation. Third computation. You see clarity is only small amount is added. This is sigma 1 times U1, V1 transpose. Sigma 2 times U2, V2 transpose, like that. So here itself, most of the features are available. 4.74 is sigma 1 value. If you add these two strings together, you'll get a much more clarity. Here also clarity is not clear, but here it is clear. You see, I can stop at this stage. Yes, this sigma value is 0, sigma value is 0. Only this much computation I have to do. So that is about digital processing or compression, image compression. You see these 4 images. This is a well-known picture. Of course, I just took it from the net. This image I want to send. If I do rank 10, reducing to rank 10 means almost all the features I want. This image, not clarity. This is rank 50. reduction 50. So the somewhat clear now, almost all clear. Your budget is not good, your facilities are less, you send this image, satisfied. You have more amount, people now you're depending on your customer, you send this image. This is 200, rank 200 image. So it's almost, but you see it's not that clear even compared to this one. This is the actual image, this is rank 200 image. That's it. So that's the idea in general. And now suppose you want a color image, what you do? I'm talking about gray scales, black and white image. If you want color, you know that color is consisted of blue, RGB, red, blue, green. So whatever M by N, you have to multiply with 3. And persistence of vision, continuous image means you have to multiply with 16. 16 image per second. You just imagine the amount of data. Every second you have to send this one. So the processing, if you are, unless otherwise you apply some good technique, your image, your transmission will not be smooth. Your amount involved with this one is more. So if you want to have optimum expense for this one, you have to apply math, better algorithm. Even now, you have this area domain has improved, but still people are searching for better algorithm. So there is a scope for research. Come with a new idea. It may be entirely different. You enter into this domain, come with a new idea and sell your idea. You will become millionaire. If you work in some institute, you will get some salary. Your salary will not cross more than 3 crores, whatever salary you are getting, mostly. But if you develop something $1 billion, you'll come with an overnight. It's not overnight effort, lifelong effort, but produce something good. Okay? All these concepts are available in these references. You can go through that and thoroughly read. Thank you so much. Focus on, in nutshell, focus on dimensionality reduction to improve the process, image processing and kind of thing. So thank you one and all again. Thank you.
Participants, any questions or any clarification? Thank you so much, sir, for your excellent presentation and for sharing your knowledge and expertise with us today.
Hello. So, thank you for the nice information. You told about matrix transformations. So, on the other way, we have bilinear transformations. Bilinear transformations in analytic functions. So, since you are working in transformations, I have the curiosity to ask, matrix transformation is the advantage over bilinear transformation?
That is a different idea.
Okay.
Because both way you can debate and you can come back to action. And mostly some domain you want to control and you convert actually.
Okay.
Some boundary. You
Yes.
want to transfer. So the best of my knowledge I'm talking about, you have a boundary, but it's very complicated boundary, so you cannot work.
Okay.
So you just transform to non-boundaries using a suitable transformation, but you want to convert the result in the original domain. So you can come back.
Okay.
You can come back to the actual boundaries and domain. That's a basic concept on bilinear transformation. Both way it will work. And multilinear transformation is also, I'm not that aware of this particular concept, but that still have a lot of contribution.
Okay. Sir.
Okay, thank you.
Thank you, sir.
That's a complex analysis.
Yeah. Thank you, sir.
Any further question? Thank you so much.
Thank you so much, sir, for your excellent presentation and for sharing your knowledge and expertise with us today.
We are truly honored by your presentation and presence. We humbly request you to stay on the podium as we would like to present the certificate and a gift to you. Thank you for sharing your expertise in the session.